this talk, I will present a joint work with Eric Cancès, Gaspard Quemelin, and Antoine Lévy from the École des Ponts Paris Tech. And I will try to derive error bounds for properties in electronic structure calculations. So, as you're probably all aware of, electronic structure models, such as density functional theory, are widely used as they offer a good compromise between accuracy and computational cost when it comes to simulating molecular and crystalline systems. And so, among others, these models offer an accurate prediction of many properties, starting with energies and forces that would be put, for example, in molecular dynamic simulations. And so in practice, we only compute approximate solutions to the problem we want to solve. And so we also compute only approximate quantities of interest. And so the question I would like to look at in my talk is how we can estimate errors on such quantities of interest. And so this to answer this question, what we have to do is to understand how the errors on the solutions for a given problem pass on properties computed from these solutions. And so in this talk, I will focus on the discretization error, also called basis set error. Okay, so the outline of my talk will be as follows. So I will start with some introduction, and then I will try to present how to do error estimation in a very generic framework, and also how to do error estimation on quantities of interest. And then I will apply it to our specific case of density functional theory. Okay, so I'm sure most of you know all of this, but so the problem I would be interested in this presentation is the ground state problem using the Concha model. And so this problem is a minimization problem under constraints. And so mathematically, if we write the Euler-Lagrange equations of the problem, we obtain a nonlinear eigenvalue problem to solve. So specifically M nonlinear eigenvalue equations, where M is the number of electrons in the system. And so the operator that has to be diagonalized is the Hamiltonian, and one of its main features is that it depends on the exact density of the system. So that makes the problem nonlinear. And so to solve the problem in practice, we first need to discretize the problem. So using, for example, planewaves or Gaussian basis sets, and then solve this nonlinear eigenvalue problem using an iterative procedure called self-consistent field algorithm. So the idea is to start from an initial guess, and then at each iteration solve a linear eigenvalue problem. And so taking in the constant potential here, the density computed at the previous step. And so after a few steps, this algorithm will hopefully converge, and then we basically stop the procedure when two following iterates are close enough. Okay, so this is when we have a finite number of electrons in the system. For crystals, it's a bit different since we have we are dealing with an infinite periodic system with a Hamiltonian, which looks a bit like this, but here the potential is periodic, but in fact, this is just equivalent to study a family of Hamiltonians, which are indexed by what is called a K point, which lives in the Brillouin zone. And so at the end, we are looking at several problems of this type. And so after all, so when we compute properties, we usually integrate over the Brillouin zone. So for example, the density of states is defined as with this integral here. And in practice, this integral is approximated with a finite sum over the Brillouin zone. Okay, so in a way, between our solution, like the solution for our the problem we are looking at, and on the other hand, the computed solution, there are several approximations of different natures. And so to detail them a little bit, so we have first what I call the model error, which contains, for example, the errors coming from using the potentials and a particular choice of exchange correlation functional. And so regarding these 2 points, I really strongly recommend you to watch François Gigi's talk. Then there is the k-point sampling. And so there was a talk by Ting about this at the beginning of the workshop. And so there is then the discretization error, which I will talk during this talk. And then there are other errors, mainly coming from the SCF error, so which is usually called the algorithmic error, and then something like floating point errors, which is usually called numerical error. Okay, so at the end we have this solution, and we can wonder how large is the total error, and then also how large is each error component. And so answering these questions is useful for at least 2 reasons. So the first reason is that it would allow to be able to certify the precision of the results, so adding basically error bars to the results that are obtained, and then also to optimize the computational resources. And so in a way, minimize the computational cost that is needed to obtain some accuracy. And so, for example, it's in a way, if the k-point sampling error is huge, it doesn't make sense to use 2 fine discretization bases, because the main part of the error will come from this k-point sampling. So we should increase the k-point sampling parameter instead of the discretization parameter. So this is the idea. And so to obtain such error bounds, so the idea is really to derive an inequality between the the error, so the exact solution and the approximate solution of the problem, and to bound that by something that will be computable. And so I made a small wish list of such an error bound. And so let's say a dream error bound should have a few properties. So it should be at least, so first it should be computable. Second, it should be guaranteed. So, and if not guaranteed in all cases, at least we should be able to know whether the bound is valid or not. The bound should also be close to the real error. So this is called efficiency. And so, for example, if the bound is something like 100 or 1,000 times larger than the exact error, then the bound doesn't give us any meaningful information. So this is why it should be close to the exact error. And then it should be cheap to compute and allow for adaptivity. And so in the precise work I will be talking about today, we focused on 2 different things, which are the efficiency and the computational cost of the bound. Okay, so let me now try to explain how do we do this in a very generic setting and using an abstract formulation of the problem. So let's say we want to solve some equation r of x equals 0, and that there is a solution x star. So for example, if we look at a simple eigenvalue problem, then the unknown will be something like the eigenfunction and the eigenvalue, and the residual will be, so the equation would be something like minus Laplace plus v phi minus lambda phi in our context of Schrödinger operators. Okay, so then the residual of the problem, which is this r of x, is 0 only for the exact solution and is non-zero in general. And so the whole idea of this error estimation is to try to link the residual of the problem, which gives an information on the error on the equation, to the error on the solution too, so 2x minus x star. And so the basic idea here is to perform a Taylor extension of the equation close to the exact solution. And so this gives that the residual at first order is equal to the differential of the residual applied to the error. And so if we can invert somehow this equation, what we obtain is that the error at first order is equal to the inverse of the differential here applied to the residual. And you see here that on the right, the expression here does not depend at all on the exact solution. It only depends on the approximate solution. So in principle, it should be computable. Numerically, this is usually very expensive to compute. So it's not that easy, but in at least written like this, it doesn't depend on the exact solution. Okay, so now if we look at a quantity of interest, so let's call it A, then the error between the approximate quantity of interest and the exact one, we can, in the same way, perform write down a first order Taylor expansion, and then we obtain this expression for an approximation of the quantity of interest error. And so in a way, to estimate the error, we just need to estimate this quantity. And a possible trivial bound for this would be to take out all operator norms and compute the norm of this differential here times the norm of this differential here times the norm of the residual. But of course, this will probably highly overestimate the error, and we will see that in a bit later. Okay, so then, I mean, this is an approximation of the error. This is by no means guaranteed, but in fact, there is a way to make these bounds guaranteed using the inverse function theorem, or also called Newton-Kantorowicz. I think this theorem has quite a few names. You can find it in this book by Carlos and Rapaz, for example. And so what this theorem says is that if the differential of the residual is an isomorphism, so it can be inverted, and that this condition here is satisfied, then the problem has a unique solution so basically we have our approximate solution, and we guarantee that there exists an exact solution of the problem within this ball. And this ball has radius 2 times the inverse of the differential times the norm of the residual. And so the second assumption that needs to be satisfied here amounts basically to control the second order derivative. So here we have the variation of the differential. So in the overall, it amounts to controlling second order derivatives. And so in a way, we have lost a factor 2 in the battle, but this is what's required to obtain a guaranteed bound at the end. Okay, and so in a way now, we just need to apply this to DFT, but this is not that easy, and for several reasons. And so one of the reasons is that the structure of the problem is not too easy to write in this form, because there are constraints and degeneracies, in particular between the eigenvalues and the orbitals. And then another point is that computing the inverse of the Jacobian is in general very costly, and so we cannot really do it on a regular basis. And then the choice in the norm in this inequality plays a really big role in how much we will lose by writing this such an inequality. And so we have to think carefully of what norms we should use. And then when we look at the errors in quantities of interest, especially the inequalities that we have may be suboptimal. And this is what I will show later. Okay, so in the following, I will consider the discretization error. And so this is mainly what you can find in this preprint here. Okay, so first, in order to simplify the analysis, I will start by stating the ground state minimization problem as a minimization problem where we look for orthogonal projectors instead of the orbitals. And so, I mean, the correspondence is just that the orbitals that are eigenstates to the quantum problem span the space that on which this projector. So this is the range of this projector, basically. And so what the problem we are looking at is the minimization of this energy, where P is an orthogonal projector of rank the number of electrons in our system. And so the energy written in this form is composed of two main parts, let's say. So one part is trace of H0P, where H0 is the linear part of the Hamiltonian. And so it contains the Laplace operator, local potential and non-local potential, and then a non-linear part of the energy, which contains the Hartree and exchange correlation part of the energy. And so the link between the Hamiltonian of the quantum equations and this energy is that the Hamiltonian of the quantum equations is just the gradient of the energy. Okay, so then we discretize this problem. So we look at the minimization of this energy on so P being a projector, where its range is in this discrete space. And so we chose to use plane waves. So this approximate space here is composed of all plane waves which have kinetic energy less than chosen cutoff. And so to simplify the analysis, we will consider a reference problem that is also discrete. So the reference problem, which we'll consider as the ground truth, will be the solution to this minimization problem, where we take here an energy cutoff that is way larger. And so in the end, if we denote the dimension of this fine space by a capital N here, then the manifold, the constraint manifold, is the space of P that are matrices and which are orthogonal projector of rank the number of electrons in the system. Okay, so now to get back to our residual equation, we need to write down the first order optimality conditions of this problem. And so we basically need to write down that the gradient of the energy is orthogonal to the tangent space of M, of the constraint manifold. And so we can do that. So we can express what the tangent space look like, and then we can write what the residual equation is. And so basically our optimality conditions were like this. So here in red. So what this comes down to is that the Hamiltonian needs to commute with the orthogonal projector that is the solution for the problem. And so if we write down these optimality conditions in terms of orbitals, we, of course, obtain the quantum problem I talked about at the beginning, which is so the resolution of this nonlinear eigenvalue problem. And so here, one important point that I want to make is that we did all the analysis with orthogonal projectors, but then all the practice is done with orbitals. And the reason for that is that theoretically, it's easier to deal with projectors because, for example, the projector solution is unique if the minimizer is the minimum is non-degenerate, which we will assume here. Whereas the orbitals are defined up to a unitary transform. So they are non-unique. But then, computationally speaking, the projector is a very large matrix, whereas the orbitals is just a list of the number of electrons is a list of vectors, and the number of these vectors is the number of electrons in the system. So it's way less expensive to store. And then there is a well-established correspondence between those objects. So we can write down easily the projector in terms of orbitals. And then we can also write down the minimization problem in terms of orbitals or projectors as I showed. And we can also characterize objects in the tangent space with kind of equivalent vectors. So there is really a one-to-one correspondence between objects in that are big matrices and orbitals. And so, for example, for the residual, so a priori the residual is a large matrix, but we can write down this correspondence, and what we obtain for the residual are the kind of the residual vectors that we would obtain if we would consider the residual of the quantum equations. Okay, so then to go to obtain an error estimation, we need the first order expansion of the residual. So basically, we need the second order geometry of the second order expansion for the energy. And so this was done in this paper by Conseil-Kellner and Levitt. And so there is the expansion of the energy can be written as this E of P is equal to E of P star plus some scalar product. And here L star is a super operator. So it's a linear operator on the matrices of size n by n. And this is something that we can write down and compute. So the assumption that we make is that this operator is strictly positive, which requires to look at a non-degenerate minimum. Okay, and so this super operator here is composed of two parts. So the same thing as before. So we have the part that comes from the linear part of the Hamiltonian, and then the nonlinear part. And so similarly here we have these two different parts, one that come from the linear part and the nonlinear part. Okay, and so if we write down the residual expansion now, we have that this so the residual at first order is equal to this operator, so this super operator applied to the projection onto the tangent space of the error between the exact and the approximate. So the approximate and the exact projector. And so in fact, in the asymptotic regime, so when P star is close to P, the error between the projectors is equal to the projection of the error onto the tangent space. So we can replace in this expression this projection by just the difference. And so at the end, we obtain this first error bound, which is just P minus P star equal to the inverse of this operator on the tangent space applied to the residual. And so the first thing that we did was to check whether this error bound was good. And this amounts to look at this higher order term and see that it is in fact small. So what we did is that we checked this approximation by computing this this quantity here. So basically taking P minus this term here and see whether this is closer to P star than the original solution. And so this corresponds to basically perform one Newton step to solve the residual equation. And so what we see here is the result. So this is for silicon, and so so here in blue we have the exact error for the energy on the left and for the density on the right. And what we see is that if we look at this energy computed after 1 Newton step, we see that it approximates way better the exact energy. So this means basically that the higher order terms here are really of higher order. And so just to give you some details about the numerical setup. So Gaspar did all the simulations that I will present in my talk. And so they were done using the DFTK software, a Joule code that runs planewave DFT, and that is mainly developed by Michael Herbst and Antoine Levitt. Okay, and so now once we have this bound, we can try to, so we have this approximation of the error and we want to turn that into a bound. So we can trivially take out the operator norm of this L star here times the norm of the residual and look at what we obtain. And so numerically, we see that, so in blue, we have the exact error, and in green, we have the bound of the error. And we see that this overestimates hugely the error. And so, but that's not what's worse here. What's terrible is that the ratio between these two plots gets higher and higher. So this means that asymptotically, we don't even have the right speed of convergence. So this is really a problem that we wanted to solve. So what we found as a next idea was to choose a right metric, so to choose the right operator norm in a sense to measure these errors. And so what we did in a way was to look at, instead of just the Frobenius norm of the projector, look at the H1 norm of the error, and then here put on both sides of this operator here 1 minus Laplace half operator. And here this means that we are not looking at the residual in L2 norm, but in H minus 1 norm. And so here, numerically, what we obtain is that, so in blue here we have the exact error, and then this bound here is in green, so it's really an upper bound of the error, and we still have an overestimation of the error, but at least the two errors decrease at the same speed asymptotically. So this is in a sense already way better. And what we also see is that if we completely drop this term here and we just take here the H minus 1 norm of the residual, we see that we have something that is not an upper bound of the error, but that asymptotically approximates very well the error. Okay, so this basically gives us an approximation of the error or a bound that is not too bad for the solution, so the projector that we are looking for. Now we wanted to look at quantities of interest, and so we started with the first but still important quantity of interest, which are the atomic forces. And so the force acting on an atom J is defined like this. So it depends on the exact solution of the problem, and it's computed with this. So it depends on the variation of the local and the non-local potential in the Hamiltonian. Okay, so if I go back to the abstract estimation, so the error between the observable A for the approximate solution minus the exact one at first order will be the differential applied to the error. And so we can write on similarly as before a bound where we take out this the norm of the Jacobian times the error. And so if we take this just for the local part of the potential, we obtain this bound here. So the error between the exact approximate force and the exact force is bounded by the product of these two terms. And so numerically, we looked at what we obtain if we write down this approximation or this bound. And we see that here, so in red here, we have the exact solution, I mean the exact error, and the approximation here is in blue. And so we see that this is really, really terrible. So basically the error, and even here we haven't taken any approximation for the error. So it's just taking out the Jacobian of the force makes it really fail the approximation. And so here on the right, so we tried not to take out this operator norm and see what we have. So in red, we have the error on the force, and then in blue here, we have the approximation at first order of this error, and we see that the two quantities match pretty well. So this is already something. But then what we see is that if we replace the error here by its approximation using the residual, then we are still far off by something like 1 order of magnitude, which means that this doesn't really well approximate the error on the forces. And so the reason is that, so if we look at this here, so we have a scalar product here. And so in fact, what happens is that the residual here, since we consider the solution converged in after all the SCF iterations, the residual here belongs, is supported only on high frequencies. But the problem is that here this part, so the gradient of the forces are mostly supported on low frequencies. So here on the right, we don't see at all the low frequencies because they are completely dropped by the residual. Whereas here we have some contribution on the low frequencies that actually matter in the end. And so this is why, so our next idea was to try to use some frequency splitting. So try to separate between low and high frequencies and do some post-processing in order to capture the part here in the error that is missing to approximate correctly the forces. Okay, so this was the idea. So I won't go too much into the details, but so the idea is really just to cut the space into two parts, the discrete space and the rest. Which contains basically the high frequencies. And then to do the post-processing I'll present afterwards, we need to decompose the tension space into two parts. So similarly between low frequencies and high frequencies. And so what we do at the end is that, so we have this approximate bound of the error on the projectors, and so here we have this operator to invert. And so what we do is that we solve this problem approximately. And so if we decompose between low and high frequencies, what we do is that we approximate this part of the operator by 0, and this part by Laplace operator, which is diagonal in plane waves. So at the end, what we obtain is that we we compute a better approximation of the error. And so we really just invert this system here. And so this gives us the approximation on the high frequencies and the approximation of the error on the low frequencies. And this defines a new residual that we can use in our estimations. And so what we see is that if we look at this new estimation, so in red still, we have the exact error between the forces. And we have in green our new estimation. And what we see is that the quantities completely match. So the new bound seems to be good enough to estimate the error on the forces. And so now if we look at so this is this same kind of plot, but where we look not at the error, the comparison between the errors, but the improvement that is brought by the approximation. And so what we see here is that so here we have the approximate force minus the error bound. And so if we look at this quantity here, we see that it's way lower than the exact error. So this, in a way, this gives us that as we saw before, that the error is well approximated by this quantity here. But this is also a bound that can be used as an improved approximation for the force. So, and there is often this kind of two possibilities to use a post-processing, either as an error bound or as an improved quantity. Okay, and so we did similar simulations for, so all of what I showed was for silicon, and so we did similar things for gallium arsenide and titanium dioxide, and we observed kind of similar results. And so before I conclude, I just wanted to mention that all the bounds that we obtain are not guaranteed, but with the result I showed you at this inverse function theorem, we could work in the direction of making this bound guaranteed. It would just probably be a bit more expensive to evaluate. And also the forces are kind of a simple first observable, but of course extensions to more involved quantities of interest would be possible. Okay, and so to conclude, I have presented error bounds for quantities of interest, namely the forces in the context of DFT. And so there is really a balance to find between the computational cost of the bound and the accuracy of the bound. And so other perspectives related to this work would be to, for example, couple such an analysis with the FCF error in order to be able to balance those errors, and also look at a more involved systems such as metals. And with that, I thank you very much.